Hello. So let's look at the Commodore 64 saver, and we're going to calculate the resistor values and its trip point. So therefore also look at the data sheet and look at the formula in there so we can compare our theory. So we're also going to look at theory here also, and we have elementary electric stuff. It's not for electronics only, it's also if you are an electrician, it will also apply to you. So first of all, it's Ohm's law, it's the most famous one, and then it's Kirchhoff's, I forgot an H there, sorry. And these are for making equations, so we can build relations with the variables and the voltages and the resistors. And when you have equations, you can start solving. So for this design we have the TL431. So this one takes a reference input, and then we set the trip point on that one. It has an internal reference though, so whenever the input there is over 2.5 volt, then it will trigger. So the design is that it triggers on the upper limit using a voltage divisor, and as you can see now we are adding a feedback here to have a hysteresis, such that when the output changes, the reference will also, or the trip point will also change, such that we circumvent noise, so we don't get unreliable operation. So let's look at Ohm's law. And Ohm's law, it says that the current is directly proportional to voltage, and what that means is that whenever voltage is changing, so is also current. We are not exactly saying how much, but when we say proportional, then we are talking about something in the same direction, not exactly, but yeah. And current is also directly inversely proportional to resistance. So if resistance increase, then the current decreases though. So that's what they mean by inversely. So it's the opposite. Yeah, so voltage is then measured in volts, and current is measured in amps. So then you have a dimension there. And the relationship between these three variables is very easy. As you can see, it's just a fraction. The current is just voltage divided by resistance. And here the triangle is for remembering this formula. So when you put your finger on one of them, you will get the correct formula. So let's take an example. You have 1 volt input and you have 1 ohm resistance, and the current is then voltage over resistance. That's 1 volt, 1 ohms, and that's 1 amperes. So it's a very straightforward. Let's say we want to find R, so you put your finger over R and you get V over I, and that's also 1 ohm here in this circuit. And then we have something called equivalent circuits, and that's if you, let's say you have a parallel, 2 resistors in parallel, that means both sides are connected together. Then you can redraw it, and you have to calculate a new value. So the current will then branch into each of those resistors, and there's a formula for that. And here you have a series connection, series, and the formula for that is much easier. And the formula for parallel is sometimes you write it like this, and yeah, you see the formula. and we will look at Kirchhoff's law, how they get to that formula. So yup, Kirchhoff's voltage law and Kirchhoff's current law. So back in the 1800s there was a dude called Gustav Robert Kirchhoff, and he was a physicist interested in electrical stuff, electrical phenomena. And he had these two laws that is very famous in elementary electric. And the first one is current. The sum of current going into a node equals 0. And that's the principle of energy conservation. So here I'm starting to write it with a sum, but sorry, forget that. It's better to write it like this, so you understand what we are talking about. So the sum of all the currents equals 0. So if current goes into a node, then if you sum them up, you will get 0. So nothing is lost. So if you have a current through a node, then you will be certain that it will pass through it. And the second law, that's loops of voltage drops. So for each loop here, you can calculate the sum of voltage drops in a loop equals 0. So it's almost the same principle. But however, we're talking about voltage drops here. So here's one example for loop A, where you have the voltage drop over the resistor 1, and then plus the opposite voltage of the battery, and the sum of that is 0. So, and it makes sense though, because you have the voltage of the battery over the resistance. So, and here's another example. Let's say you have two resistors, and you have 2 volt drop and 3 volt drop, and together you will have 5 volt drop over there. So if you sum all of that together in a loop, you will get 0. And the point of all this is to get equations, and when you have an equation you can solve. So, and these equations, they are easy. They are high school math, so no problems really. So here we have one equivalent circuit, 2 resistors in parallel, and you can redraw it in this way as we talked about earlier. And remember the Ohm's law here. And the parallel equivalent is then this formula. And why? So the Kirchhoff current law, it says that sum of currents into a node equals 0. So let's put on the currents here. You have the main current going in from the battery or the voltage source. Then you have one going down into R1 and another one into R2. So let's just sum it up. And the reason for writing the negative sign here is because the current is not going into the node, it's going out of the node. So you have to be consistent. So, and here's the trick with the current law, is to replace current with the voltage and resistance using the Ohm's law. Where's this one? Okay. And you see that the voltage is the same over all of these terms, so we can divide the whole equation by V. And then, with some magic, you get this formula. Yep, so there it is. Easy. And there's a general formula for this. If you keep it in this form, you can have as many branches as you want. I have two schematics for this, or data sheets for this TL431. So, but the Texas Instruments one has more applications notes in it. So let's look at that. And here you can see the operation, or the equivalent schematic for this device. It's not completely true, so, but basically this is how it works. When the reference goes above the VREF, then the output changes. And this is how it is built up, so it's pretty complicated. And here you see a Crowbar Circuit. So this TL431 is used as a trigger for the SCR, and the SCR will then blow the fuse whenever you get a fault. But we are not going to blow the fuse. We are going to use this one. It's a voltage monitor, except that we are not monitoring, we are switching. So basically the input here, R1A and R2A, is what we have. And you can see the formula to the right, the high limit. It's a simple formula. So let's look at Kirchhoff's law and see how they get there. Okay, so English home, so maybe a little bit less concentrated. But basically we are using Kirchhoff's law to... Okay, so she's coaxing herself with the druce. Grapes, I'm sorry. Druce?
Ja, druer på engelsk.
Drapes. Nei, det er gardiner.
Jeg spiser ikke gardiner.
Grapes?
Grapes.
Yeah, grapes, ikke drapes. Okay, so here is basically the circuit that we have now. The Commodore saver, so you have 5 volt on the input. It's the power supply input, or the input that takes the power supply connection. And then whenever that 5 volt goes over the threshold, then the TL431 will trigger. And the problem with that is it doesn't go all the way down to 0 volts, so we have a second transistor there, or a P-channel transistor that helps it trigger all the way. So here is the equivalent circuit. We're only focusing on the resistors here. So the thing is that it's V reference, that's the input of the TL431, and we are only interested in that reference when that is 2.5 volts, so let's keep that as a constant. It's not constant, but if you keep it a constant, then we can solve for the power supply voltage. What is the power supply voltage when we have something happening on the output? So let's keep that a variable in our math equation. So here you have the output voltage stuff. So yeah, it's also good to have names, and let's ignore that part for now. So the hysteresis feedback. So the datasheet says the upper limit of the voltage, the upper limit of the voltage equals 1 plus R1 over R2, and all of that is is multiplied by Vref, which is 2.5 volt. So a voltage divider is basically two resistors, and the formula for that is also very simple though, so let's write it down. And also, when you have this voltage divider, you have to assume that there's no current going out of it. It's just dividing the voltage. There will be some current going into the reference, but we can ignore it. It's so small. So here's the formula, but we're not interested in V out. We are interested in V in, which is our power supply. So power supply voltage. So we solve it for V in. But what can we do then? So okay, so basically you just wrote the same thing twice, and you want V in alone, so you move the fraction over on the other side of the equation, and when you do that you have to turn it upside down. So, and if you then simplify it, it will look like the formula in the datasheet there. So it's basically a voltage divider with solved for V out instead of V in. Okay, I started out with doing KCL to calculate these resistors together and get the relationship between the voltages and the resistors. But however, I was confused because I used another circuit before, and the side here didn't go all the way up to this point and down to this point. Well, it did go all the way up here, but it didn't go all the way down here when the state of the output changes. So it's changed to 2 volt, not 0. So that's why I used, that's why I'm now skipping this part. But I will include it anyway, so this is the hard way, or sometimes the only way, but it's not necessary if you have this connection. Ingrid, in class, we don't eat potato gull chips.
No. But what about play?
No cell phones. Okay, play some games so I can concentrate.
Okay, thank you.
Okay, so we assume that the voltage is... why am I holding my hand over that? Okay, so we assume the voltage is low, so then we are looking for the upper limit. And then we know that when the output goes up, the voltage there is the same as V out. So V in is V out. So the VRF, that's the output of the voltage divider. So we can look at R4 as in parallel with R1, as you can see. And that's only for this condition, and it will be different for the other condition. So, but we are solving for V in this time, so let's do the same again as we did earlier. Just flip the equation over. So we get V in alone. So, and now let's replace the parallel sign with the actual formula. And yeah, so what I'm doing here, I'm dividing the whole equation by R2. I forgot to put parentheses on there, so I've just put it on the screen now. Sorry about that. Okay. That it. And you also remember from before, when you have the parallel circuit, you can write it like this inversely. So let's do that. So this is the inverse parallel. So then you have to put 1 over 1 over. It's just algebra, it's nothing special about it. So just make it simpler. So, yep, so that's the formula. And now what happens if we take R4 out of circuit, so we just get the normal voltage divider. So how to take that out of circuit in a formula? Then you set the R4 to go to infinity, and then as you can see, the 1 over R4 goes to 0. And then you're back to the original formula. So you see that it works. It's not a complete proof, but you can see it intuitively. So yeah, and here's the part that I left out because I used the Kirchhoff current law, and it wasn't strictly necessary here because we could simply just parallel the two resistors, but if for some reason V out is not going completely 0 or up to 5 volt or the power supply voltage, let's say it only goes down to 2 volt because of that TL431, then you have to include it and you have a more complicated formula. So that's what I initially did, so yeah. So basically what you do, you sum all those current together to 0, and then you replace current with a voltage and resistance, the Ohm's law, like we did earlier. And when you assume that V in is below threshold, then you have a condition that says V in is the same as V out. And that makes this equation much simpler, because then we can factorize it. So now it's factorized. Let's move that term over to the other side. And then after doing that, we will divide the circuit by this 1 over R1 plus 1 over R4. Did I say circuit? Equation. So there you go. Basically it's the same equation that we had before. And the same method applies to when you find the other threshold. let me show you the circuit that I have built. So here it is. So we have seen it before, but it's drawn in eagle now. And I'll put some test points on there, so we can, yeah, it's easier to measure when you have the circuit. So here you have the board. It has input connection on the left and outputs on the right. So I also made a calculation sheet, a spreadsheet. So basically I have common resistance values for R1 and R2 as columns and rows, and then you basically have the formula that we looked at. It's calculated for each combination. So you see I highlighted the one that's a 5.24 there. So that will be the one choice I will make though. So this is the formula down there. VREF, that's the one on the that I have marked there up in the formula area. 2.5 volts. And over here you can see the feedback resistance, R3, it's actually R4 though, so I can change it and all of the values will then change automatically, so I can play around with them. I think you could have solved this value making formulas, but I like to make a spreadsheet and then yeah, then I can see what fits though. So yeah, hope you liked it. So soon I will get components and I will make the board. So thank you for watching and hope you liked the video. Bye bye.